So first of all, it's my great pleasure to be here and to speak in front of you. I heard that some of you are interested in singularity formation. I'm very happy to talk about it. Also, it's my first time to India. It's been very great so far. So I'm in an institute called Korea Institute for Advanced Study. My understanding is that it's the Korean version of ICTS. We have math and physics. Okay, so the goal of these talks is to give you some introduction to recent breakthrough works in singularity formation. They are not my works, so goal is to explain the ideas and some technical parts of, let me call C alpha singularity theorem. In two papers. There are other papers as well by Tarek El-Gindi. So this work was published in 21 in Annals of Mathematics. And there is a more recent work by Diego Cordoba, Luis Martinez Zurwa, and Fan Zheng. It was published in Annals of PDE last year. So they basically proved the same result, C alpha singularity or incompressible Euler. The methods are quite different, and I want to explain both methods. Okay? But today we will just start with introducing the incompressible Euler equations. Okay. So for this introduction part, there are many textbooks which you can read. So the standard references are books by Maeda and Bertozzi. This book is maybe more than 20 years old, but still very nice reference. There's a very recent book by Bedrosian and Bikor. So everything that I will tell you today can be found in these very standard references. Okay? Because today I will just introduce you the equations and the questions. Okay, so let me start directly with the incompressible Euler equations. So here is the equations. Incompressible Euler. We have time derivative plus u dot gradient, u plus gradient t is 0, and also divergence of u is 0. So u is the velocity field, time dependent. So let me say u, okay, is u1 tx, u2 tx, u3 tx. Sorry, sometimes it's better to write the vector in column vector. Sorry. That's what I intended to do. So U is a vector field defined in R3 and some time variable t. Okay, so U is a function from time interval, say 0 to capital T times R3. And it has 3 components, so it's a map into R3. We'll only consider R3 for simplicity. Okay. So the first equation is an equation for each component of the velocity, just to make sure that the meaning is completely clear. In components, this means time derivative of uj plus, so u dot gradient is an operator, which is a summation u1 dx1, u2 dx2, u3 dx3 times uj plus dxj of p is 0. For each j, 1, 2, and 3. Okay? And thanks to Stefano's lecture, I don't need to explain. Divergence of u is 0. This is just dx1, u1 plus dx2, u2, dx3, u3 is 0. Okay? Just explaining the notation here. So in this lecture, I will immediately introduce the vorticity and derive what is so-called the vorticity equation. Okay? It turns out to be much more convenient, and it has its intrinsic meaning. So the vorticity equation. My understanding is that the vorticity equation was derived already by Helmholtz in the middle of 19th century. Okay? The vorticity of the fluid, denoted usually by omega, is another vector field, which is just the curl of the velocity. Okay? So I hope we know what is the curl. Okay? I can write down definition if you want. Okay? So it's also a vector, omega 1, 2, and 3. And by vorticity equation, I mean the equation obtained by taking the curl of this equation. Okay? You take the curl of this equation, and then the claim, non-trivial calculation, is that you obtain partial derivative of omega plus u dot gradient omega equals omega dot gradient u. So this is a non-trivial computation. So what happens is that you take the curl of this equation. Here you immediately get dt omega. If you take the curl of this quadratic term, what you get is u dot grad omega minus omega dot grad u. Okay? And curl of gradient is 0. So you see that there is no p in this equation. That's actually the main benefit of using the vorticity equation. Okay, and I really hope that the meaning of these terms are clear. So I want to just mention one thing, that many people use this notation to denote the right-hand side. And sometimes it's confusing what this means. Okay, so what do you think this means? Gradient u times omega. Yes, yes. And I'm mentioning this point because in fluid dynamics, somehow the usual convention for gradient u is that you expand the gradient in rows. Okay, that's why I wrote U as a column vector. Okay, so what is gradient of U? It's a 3 by 3 matrix where, so here's what you do. You write U1, U2, U3, 3 columns. And then you expand the gradient in each rows. X1, X2, X3. Okay. This is the usual convention for gradient U. So now what is this right-hand side? You multiply to this matrix the vector omega. And again, it's important that we write omega as a column vector. Okay. And now I'm not explaining how you multiply the matrix with a vector. But the claim, which is again non-trivial, is that this matrix product equals this derivative. Okay? They are the same. Okay? Any questions? So it has some meaning. So this is, you can see this as derivative of U along the direction of the vorticity. That's the meaning of this. And this meaning is kind of clear. You somehow stretch your omega by this 3 by 3 matrix, but they are equal. And the next point is that if you decide to use the vorticity equation, you need an equation for U, okay? You need an equation for U. So there is this small vector calculus identity, okay, which is very cute and useful. Let's say you have a vector field in R3. Is any vector field in R3? Okay. What you have is that if you take the curl twice, this equals negative Laplacian plus gradient of divergence of V. Okay. This holds for any vector field B. It's a good exercise. I'm never good at this kind of computation. So when I do it, often I get the opposite sign. I do it again, and so on. Okay. So what do we do is take U in the position for B, okay, and see what happens. So you have here curl of U. Curl of U is by definition omega. Here you have minus Laplacian U, and then you have grad divergence, but divergence of U, we want it to be 0. So that's 0. Okay. So what is the point? Point is that if we can find solution to the Laplace equation, meaning that if we know the vorticity, we know the curl of the vorticity. Solving Laplace equation means that find U such that minus Laplacian of U is a given function. Okay? That we denote by minus Laplacian inverse of curl of omega. Okay? This is just formal notation, but the point is that it has a simple solution formula, the Laplace equation. the formula in R3 is simply, T is not so relevant here, but just keep it for consistency. This operator in R3 is just integral against what is called the Newtonian potential. Integral in R3, 1 over x minus y, absolute value, curl of omega, dy dy. Okay. And the usual form that people use, so this is a correct identity, but people usually prefer to take this derivative on the kernel, which is just an integration by parts. Okay? So if you do this integration by parts, okay, I will write the result here. We get what is usually called the Biot-Savart law in R3. So what you do is you move this derivative to this function, 1 over x minus y. So there is this non-trivial computation you need to do. And then you get x minus y divided by x minus y to power 3 cross product of two vectors, x minus y and omega, dy dy. And this is often called as Biot-Savart law. Because it's the same law in electromagnetics, how you compute the magnetic field corresponding to a current. So this pair of equations, okay, is called the vorticity formulation of the incompressible Euler equations. So it's called the vorticity formulation. Okay. The first equation describes how the vorticity is changing in time given the velocity u. Okay. The next equation tells us how to get velocity from vorticity at each moment of time. You need to do this integration in space. Okay, any questions? Yes?
By telling me, okay, suppose if I know the vorticity distribution, then I can solve for velocity. But vorticity itself is depending on velocity. So are you telling by physical observations that I know vorticity? With that I know the velocity. Also,
Could you repeat the question again?
yeah. So omega itself is depending on the velocity.
Yes.
So now you are saying, suppose if I know the distribution of vorticity,
Yes.
then I'll solve for u.
Yes.
So that's the main thing. So.
Right. That's a great question. Maybe it's kind of philosophical. Vorticity and velocity, they define each other simultaneously. So the point is that we just need to understand one of them. So velocity equation just says that we want to understand how the velocity is moving in space and time. If we have that, we just take the curl of the velocity. That's vorticity. But the problem with that is in the computation of pressure. So there is a, in some sense, similar rule between pressure and velocity. If you know the velocity, you can calculate the pressure by some integral formula, but that integral formula is much more complicated than the Biot-Savart law, because that one is nonlinear and non-local. So you cannot remove the non-locality, which is the fundamental issue in incompressible Euler, but you can at least make the non-locality linear in terms of the unknown. Okay? So it's just a change of viewpoint, because vorticity is, of course, just curl of the velocity. But this is actually the fundamental observation of Helmholtz. What is this observation? If you know the vorticity, you get the velocity uniquely for incompressible flows. This is no longer true for compressible flows. Okay? So the fundamental observation is that for incompressible flows, vorticity uniquely decides the velocity. Of course, there is a caveat here, which is hidden in the solution of the Poisson equation, is that I'm always assuming in these talks that the velocity is decaying at infinity. Okay? I will always assume that. Any other questions?
The question is clear. Is there any condition for Biot-Savart law, for example? It's a closed domain with no slip condition. Is this Biot-Savart law valid?
Oh, it needs to be completely changed. And there's no longer a simple formula like that. Yeah. Thank you for the question. So now we are considering domain to be just whole space R3. If it's replaced by some other domain, say open set in R3, the formula is no longer true. Yeah, basically. Oh, that is still true. It's just that formula is much more complicated and potentially not explicit.
Flow through nozzle, ideal flow through nozzle.
Okay.
In the case of ideal flow through nozzle, we cannot retrieve velocity from vorticity alone.
If there is some like boundary condition or velocity, that's a different story. Yes. Yes, it can be seen as a boundary condition issue, which is also here in R3. Here, R3 boundary is at infinity. So unless we give some condition at infinity for velocity, this is not really true. But I'm giving it that velocity is 0 at infinity. Yeah, that's why we can, do it. Okay, great. So to proceed further, let me now explain to you what is the initial value problem. I just do it here. So in this talks, we are interested in the initial value problem. It simply means that we want to find a solution to the vorticity formulation given initial vorticity. Okay. Given sufficiently nice initial vorticity, okay, in R3, sufficiently nice. I will explain the conditions later. Find a unique, nice solution omega now is function of t and x. This is just a function of x, satisfying the vorticity equation. Let me call just star with omega at time 0 equal to omega 0. And then there is a question of local versus global. Okay, so question about local versus global. So this is another question, which is that given initial vorticity, omega 0, can we find a solution to the vorticity equation for every t? Okay, or not? That's the question. Can we find a solution for, let me say, solution in 0 to t times R3 for every t positive, or we cannot. That means that there is some limit, say t star, okay, beyond which there is no solution to the vorticity equation anymore. And that is roughly meaning of finite time singularity. Okay? But this concept will become more clear later. So the initial value problem for the vorticity equation is very classical. The first work was in 1920s, okay, by several people. So I will first state the very classical result. Okay, so the classical result is that yes, you can find a solution, but only for some finite time. Okay. So let me state it like this. Let omega 0 be divergence free. That's necessary for this to be the curl of something. I will not write it down. So let this be divergence free, and also C infinity and L1 in R3. Okay. So infinitely differentiable with continuous and bounded derivatives. L1 just means that it is an integrable function. You need to impose some decay at infinity. Okay. Then there exists some time and a unique solution to vorticity equation, omega satisfying is C infinity in time and space, and also integrable uniformly in time. And satisfies the initial condition. Okay. So the statement is very simple and it's the desired one. If the initial velocity is nice, infinitely differentiable and integrable, this is just some decay assumption. L1 itself is not so important. Then there exists some time and a unique solution within that time. And again, it was proved already in the 1920s for the vorticity equation. So let me introduce some additional function spaces while explaining how the proof is done. Okay? So here an issue is that C infinity, as you may have heard, is not a Banach space. It does not have a norm which gives the size of C infinity functions. So it's not easy to work directly in C infinity to get this existence result. Okay, it's a technical issue. Okay, so the natural idea is to use instead CK. Okay, CK space means space of functions which have up to K partial derivatives and continuous and bounded. Okay, but there is an issue with CK. And that's why Felder introduced the Felder spaces. So I actually learned this last year. Felder introduced his famous spaces to basically prove this theorem. I didn't know it until last year. So the issue, very briefly, or issues, C infinity, not Banach. So you want to represent C infinity as an infinite intersection of Banach spaces within which the equation has a solution. So CK is a natural choice, right? Because then we can represent C infinity as an infinite intersection of CK. Okay, but CK has a problem. CK has a problem. That's actually one of important issues in these talks, but CK is not good. For every integer k, if k is an integer. So why is it not good? So you can already see it from the vorticity equation. Let's say we want to estimate how fast the maximum norm of the vorticity grows in time. Okay? This is time derivative of omega. So this governs how much time change the maximum can occur. This is just derivative. At the maximum point of omega, derivative is 0. So you can neglect this. Okay? So the change of maximum of omega is governed by this. Okay? So in terms of inequalities, if you want to understand how fast the maximum norm, or C0, in space is changing, you need to understand this product, which is basically bounded by C0, gradient U, C0. However, it's not good because this is not bounded in terms of maximum of the vorticity. Okay. But the reason, in the first place, we could have expected such an inequality is the following. Omega is gradient of, curl of the velocity. Okay. So in terms of the number of derivatives, it's natural to expect that gradient of U, this 3×3 matrix, all the components in maximum is bounded by maximum of omega. But that is simply false. Okay. So I'm not really sure if it's a good idea, but we say this is definition. We say F is C0 R3 if F is bounded, uniformly bounded and continuous in all of R3. And we write F C0 or F at infinity as supremum of f of x in R3. If f is a vector, this is absolute value of the vector. And this is same thing as at infinity. Okay. So the point is that this issue is fixed if you introduce the Hölder spaces. Okay. So he introduced these CK alpha spaces, alpha between 0 and 1. And proved this existence and uniqueness result in CK alpha spaces. So K is an integer, at least 0. Okay. So Hölder's theorem is the following. You fix some K and alpha. K is an integer. It can be 0. And alpha is between 0 and 1, but not including 0 and 1. Okay. If initial vorticity belongs to CK alpha and L1 R3, then there is T and a unique solution to the vorticity equation where the vorticity is now CK alpha. Okay. So I will not write down everything again. Then it is just T and a unique solution, omega, which now belongs to bounded in time with values in CK alpha, and it's continuous still in the L1. And this can be used to imply, because this works for every K, this can be used to imply the classical result, the C infinity result. The point is that C infinity is also the intersection of CK alphas for any fixed alpha between 0 and 1, right? And now you have this inequality if you replace C0 by C alpha. But alpha needs to be always strictly between 0 and 1. Okay. This, this I can explain in more detail maybe tomorrow, but the argument is that if you study the evolution of, say, omega squared, okay? This is the equation. At the maximum of omega, derivative is 0 because you are at the maximum. So this term vanishes at the maximum. That's why you only have the right-hand side. Okay. That's a very good question. Okay. And the whole point of these lectures is to discuss whether this t can be taken to be infinity or there is a limit. There's a limit, say t star, after which there is no nice solution. Okay. That's the whole point of these lectures. And regarding this issue, there is the so-called Bill-Kato-Maeda criterion. Probably this was known before this result. This was only in the 80s. What is the statement? The solution, which we know that exists for at least some t, okay? The solution cannot be continued after some t star if and only if so this terminology in this, it's implicit that you have the solution for every t before t star, okay? So you can calculate omega for any t strictly before t star. If you take the maximum, it can be at infinity or C0 is the same. Let's say at infinity because that's what people write. If this diverges to infinity as t increases to t star. That's not necessary. Yes, it's a very good point. It's not necessary. So it says, so one direction is kind of clear. Let's say this happens. Let's say there exists some t star such that before t star we have the ck alpha solution, okay, such that the maximum of vorticity becomes infinite. Then it is clear that there should not be ck alpha solution after t star because at infinity is infinite. Okay? It's the other direction which is non-trivial, and that's what they prove. Strictly speaking, ck alpha solution can stop existing with finite maximum, but just infinite ck alpha known in principle. Okay? Say derivative. Maybe the derivative of omega becomes infinite, but maximum stays finite. So definition of singularity in a strict sense means that some derivative, some finite order derivative becomes infinite. That's the standard definition of singularity. But what they proved is that for any high order derivative of omega to become infinite, it is must be the case that the maximum becomes infinite. Okay? So this is very important for numerical purposes, for instance. Because when you do numerical computations for fluids, there's so much instabilities that the gradients or higher order derivatives of the vorticity grows extremely fast. So usually it's hard to distinguish whether high order derivative is becoming infinite or becoming just very large but finite. But rather, maximum of the vorticity numerically is much easier to calculate relatively. You just check whether this becomes infinite or not. That's equivalent to solution remaining in C infinity. Okay? So while the proof is very simple, conceptually it has a lot of stuff. Okay. Okay, any questions?
Space is integer, there is an issue, right? But that can be overcome if you use older spaces.
Yes.
So why does it help exactly in that place?
Yes. So the reason is very simple, and that's what I will write now. So the key estimates. The first one is very simple. It is just the statement is that gradient of u, if you measure this size in ck alpha, okay, this is bounded by some constant which depends on k and alpha times omega in ck alpha. For every k integer at least 0 and alpha between 0 and 1. Okay. So this is the difference. So it could be a bit confusing. But if we redo this computation in C alpha rather than C0, okay, it needs to be done carefully. Let's do it next time. If you do it in C alpha, you will have C alpha here. You have the product rule, you have C alpha and C alpha. But this in C alpha is bounded by omega in C alpha. So what you have basically from this is that time derivative, we will do this computation maybe tomorrow more carefully. Some constant depending on alpha times omega C alpha squared. Okay. So this is differential inequality. What this means is that if initially this is finite, there's some time interval, which is basically 1 over this coefficient, during which this remains finite. Okay. That's how you prove.
When here it is not true because you only have information for curl, not the entire gradient. So
Yes.
divergence information is missing in a sense.
No, it's just yes, the spaces are different. Spaces are different.
So you are missing there. Why that is okay here? I mean, there you have only information on curl. So of course, you cannot estimate the entire gradient, right? whatever information you have, right?
So we are supposed to have all the information because omega uniquely determines U. This mapping is well defined. It's just a matter of in which function spaces the map is continuous map. Yeah. So if you have omega, gradient of U is already uniquely defined, but the question is just in which function spaces is this mapping continuous? It's continuous in CK alpha, but not in CK. But this is kind of well known, and maybe I can give you a further remark. Okay, so remark. I can even give you an example, but I might make a mistake. So it's well known that if you consider the Poisson equation, if you recall, that's how we found out the Biot-Savart law. If you consider the Poisson equation, let me say Laplacian psi is f. Okay, in R3, say f in C0 R3, even with compact support, this is just to remove issues at infinity. This does not imply, unfortunately, that psi is C2, even locally. Okay. You do not get two derivatives in C0. Boundedness of? Exactly. So we will prove this estimate tomorrow for slightly simpler operator. This is exactly Calderon-Zygmunt estimate. Okay. So the second key estimate is the following. Time derivative of omega, say in CK alpha, is bounded by, so here is the, I will first show you a naive estimate and a better estimate. Naive estimate is this, with some constant depending on K and alpha. This is true, but this is not good enough. Because here is a slightly delicate point, which is that how do you deduce C infinity existence from CK alpha existence? If you have C infinity data, you want to apply this statement for each K and get a CK alpha solution and then use uniqueness. Here, the issue is that T may depend on K, right? So this by itself does not necessarily imply C infinity existence. Imagine that your solution was initially C infinity, but remains in CK only up to time 1 over K, right? If you only use this kind of estimate, that is definitely possible. And in some sense, the correct estimate to do, you still have dependence in C K alpha, but now it's linear. the nonlinearity comes only with the maximum of the velocity graph. This is the correct estimate. So this is the key quantity. Which is just the Lipschitz norm of the velocity. We know it's a fundamental quantity for solving differential equations. And the final key estimate is so-called logarithmic interpolation inequality, which says that gradient of u at infinity is bounded by vorticity at infinity. So I told you that this is false, okay? So this is false, and this was the starting point of Felder spaces historically, but it is correct if you add a log log of the C alpha naught. And let me check the precise version here. Don't worry about this L1 stuff. It is minor. With power alpha over 3. And here you have at infinity 1 plus r. Okay. And we can just put the semi-norm. So semi-norm is just defined by supremum of x not equal to y, x minus y alpha, omega x minus omega y. Okay. And log plus, this is also not important. It means that you make this 0 when this is larger than 1. It's not important. You can put log and it's okay. So in these key estimates, you notice that the first and third one are just some harmonic analysis estimates. They are in some sense completely independent of change in time, because these two holds for each fixed t. And they are just kind of well-known estimates in harmonic analysis. Only the second equation actually use the time-dependent equation. The first and third just use the Biot-Savart law. Okay? So the claim is that if we have these inequalities, basically you can prove everything here. Okay? Okay, any questions? Yes, unfortunately, yeah. Constant always depends on k and also alpha. Yes, this one is actually yes, thank you very much. Yeah, thank you very much. Yeah, it depends on alpha. Yes, because if it didn't, then you can take the limit alpha going to 0, and then that estimate is false. So you can take actually 1 over alpha. So you can take alpha to be 1. That's totally fine. You are using C1. But you cannot take C0 because then this is in. Thank you very much. Hey, Kazuo. Yes? It's a great question. Unfortunately, I do not know. Yes. Yes. Okay. Any questions?
Guarantee velocity flow. This BK, this guarantee velocity flow.
Velocity?
No, the velocity going to infinity. Will velocity go to infinity?
Oh. It's not known whether there is singularity of Euler where velocity goes to infinity or not.
Even after what is the infinity?
Velocity is maybe finite. And it is finite in those results where they prove singularity in the maximum of vorticity, velocity remains finite. That's a great question because you can consider the incompressible Navier-Stokes equations, right? So also there is a similar criterion for singularity of Navier-Stokes. So in the 60s or even 50s, Hopf proved that for Navier-Stokes singularity, instead of vorticity, the velocity maximum should go to infinity. That's for Navier-Stokes. But for Euler, velocity can remain finite. But that is not enough to solve the equation. That is not enough. Okay, other questions? So briefly mentioning the works that we will eventually get to, the singularity, C alpha singularity theorems. Very recently, only very recently, it was proved that in this class of solution, when K is 0, we have positive time and a unique solution within that time. It was shown that some of these solutions actually become infinity. Okay? So you see, it was really only very, very recent that first examples of singularity was found in R3. So before doing that, I think we can just conclude by how to actually prove existence of solution. Okay, I will discuss these estimates tomorrow. Okay, but the question that I want to discuss for maybe 10 minutes is how do you actually prove the existence of solution to the vorticity equation? The idea is very nice and kind of related to what Stefano did this morning. It's just solving transport equation. Okay. So existence of solution. We take K to 0 for simplicity and fix some alpha between 0 and 1. Okay. What we will do is we will build a sequence of solutions, okay, by an iteration solving the transport equation only. Okay. So here is how it goes. Assume that for some positive t and a vorticity at level n is given such that omega n at time t, you take the C alpha norm, we can also take the L1. It's probably waste of time, but strictly speaking, you need some decay. Supremum in time is bounded by some m. Assume that you have vorticity omega n with this bound. Okay. What we do is we define un, velocity at level n, using the Biot-Savart law. Okay, using Biot-Savart on the same time interval. Okay. This means un by definition is this integral here. What do we do next? We solve the following transport equation, or transport and stretching equation. Solve time derivative of omega n plus 1. Now this is what we want to solve for, plus un dot gradient omega n plus 1 equals omega n plus 1 dot gradient un with the same initial condition, omega 0, which is given to us as a C alpha and integrable function. And when we solve this, omega n plus 1, we make sure that the same estimate holds with n replaced by n plus 1, with same t and same m. Okay? So pictorially, it's very simple. And at the initial layer, we define omega 0, the zeroth vorticity, for every t to be just omega 0 at x. This is initial step. Okay. At the initial step, capital T can be infinite, and m is just the norm of the initial data. In the later steps, we will need to adjust t and also m a little bit. Okay. Okay, any questions? So pictorially is very simple. Initial iteration is just constant in time. You use this to define the zeroth velocity. You use this to solve omega 1. But how do we exactly do this? We do this by finding the flow of u. And then using the flow, we can get omega 1. So I personally prefer to use phi, but Stefano already used capital X, which I also like. Okay. So X x0 is the flow of u0. And you go like this. Okay, so how does having a flow helps in solving this equation? Okay, so in general, let xn be the flow of un. Okay. So what is the point here? For omega n, we have this bound. From this bound, we have supremum in time as a consequence of that bound for vorticity at level n. We have this bound, gradient of u, C alpha, is bounded by some constant depending on alpha times m. So just to be clear, when I write C alpha, it is always the sum of at infinity and the C alpha semi-norm, which I denote with a dot. Okay, that's standard definition of C alpha without a dot is sum of maximum and the modulus of continuity. Okay. So this is finite. From the key estimate number 1, using this inductive assumption. So in particular, we can find the unique solution of this ordinary differential equation. Xn, by definition, is the flow of un. Okay. Now, what's the point? The point is that if we define omega n plus 1, the next guy, okay, if we define this by xn dx equals gradient x dx multiplied by omega 0 x, then this solves. So this I will write as star n. So let's just check one thing. Take t to be 0, okay? If you take t to be 0, this is just x, okay? It's just x, and this is 0. If t is 0, this capital X is just x. So the gradient is the identity matrix. So again, what is this? This is the 3 by 3 matrix where we expand the gradient in each row. Okay? It's matrix multiplication. So this is trivially true at t equals 0. because that's the initial condition. And the non-trivial claim is that this formula solves this equation. And this is sometimes called the Cauchy formula, okay? Because he knew about this formula. So what's the point? The point is that now we can use this formula to verify this inductive assumption at level n+1, okay, using the formula. But of course, to do that, we need to estimate gradient x. Okay? But we can do that. And if we do that, this chain closes, and we obtain a sequence of functions omega n, which is uniformly bounded in this sense. And then what we do is the following. So here is some small point that I still want to make. It's not enough to just use a compactness theorem like Argellas, Koley to find the subsequent limit. I claim that it's not enough. Why? So now what do we have? I mean, assuming that we can easily estimate this expression, we have a sequence of vorticities, omega n, which satisfy this uniform bound for every n. So by Argellas, Koley, for example, there is a subsequence which converges in C0, say, okay? And the velocity gradient also converges in C0 because the velocity gradients are uniformly in C alpha as well, okay? So there is a strongly convergent subsequence. Sorry? The C alpha norm cannot increase in the limit. So the limit is C alpha function. But that's not enough simply because here we have n and here we have n+1. Right? So if we know the strong convergence for some subsequence, say nk, what we have is that we actually have nk, 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 nk minus 1, nk minus 1. They do not need to converge in any sense. Okay? So you cannot use compactness to finish the proof of existence. So what you need to do is you actually need to prove that the sequence of vorticities is a Cauchy sequence in some weak norm. Okay? You can do it in C0, actually. Okay? You show that it's a Cauchy sequence in some weak norm, and then use compactness in C beta, where beta is between 0 and alpha, to find the limit. And then now the limit, you can show it's a solution to the vorticity equation. Okay? Because now the limit holds for all subsequences. So the main point was that there are some small issues to be done, but the idea is that you can prove the existence of solution using what I call the transport iteration. Okay? You have your approximate solution that defines the velocity field. You again solve the transport equation with updated velocity fields and repeat. Okay? And in the limit, you obtain a solution to the vorticity equation. Any questions? Yes? Sorry, can we use? Oh, yes, yes. Yes, we can certainly do that, actually. Yes. So one can reformulate this as finding a fixed point of some mapping defined in C alpha. Yes, but if you do it carefully, it will give the same existence result. Yes. So if you have questions about details in existence, I can happily talk to you, and I will not discuss it further. Rather, tomorrow I want to discuss some of these estimates and also discuss some simplified model for 3D Euler equations where singularity is kind of easy to prove. Okay, that's it. Thank you.